Hi everyone, today we're going to be talking about De Morgan's laws. Now, these are logical equivalences that are quite useful. But before we get into it, I should tell you exactly what a logical equivalence is. It means that if we created a joint truth table, then the two columns corresponding to the two equivalent propositions will have the same column. Now I'll show you what De Morgan's laws are, and after that I will prove that they are in fact logical equivalences. So the first one is P or Q negated is logically equivalent to not P and not Q. And the second one, it's the corresponding one but with the conjunctions and disjunctions swapped. It's not P and Q is equivalent to not P or not Q. Now, why are these useful? They're useful because of a property of logical equivalences. They're useful because if we want to prove one, it suffices to prove the other one. And that's helpful in math because sometimes we might not be able to prove one of them, but we might be able to easily prove the other one. Now that we have the preliminaries out of the way, let's actually prove De Morgan's laws. The first one will need a truth table starting with P and Q. I'll write out all the gory details. P or Q, not P or Q, not P, not Q, and not P and not Q. So we've got a whole bunch of columns over here, but there's only going to be 4 rows corresponding to 0, 0, 0, 1, 1, 0, 1, 1. We can write out the negation columns for not P and not Q now, which are 1, 1, 0, 0. We're just flipping all the P's. And now we flip the Q's to get 1, 0, 1, 0. Now we go back to P or Q to get 0, 1, 1, 1. And now we flip all these to get 1, 0, 0, 0. And in the final column, we have 1, 0, 0, 0. Now we compare this column with this column, and we find that in fact they are identical. So these two are logically equivalent. Let's do the same exercise with the second De Morgan's law. We have P and Q as the atomic elements. We have P and Q, then we negate that. There's not P, not Q, and not P or not Q. Let's fill out the columns now. The possibilities once more are 0, 0, 0, 1, 1, 0, and 1, 1. We flip them again to get the negation columns. 1, 1, 0, 0, 1, 0, 1, 0. For P and Q, we get 0, 0, 0, 1. We now negate it to get 1, 1, 1, 0. And in the final column, we have 1, 1, 1, 0. So if we compare this column and this column, we find that they are identical. So this is logically equivalent to this. So that proves De Morgan's laws. But this is not the end of the story. We can actually generalize this to n propositions, where n is greater than or equal to 2, a conjunction or disjunction of n propositions. Not mixed conjunctions and disjunctions, but all conjunctions or all disjunctions. Let's get into that now. The hard part is actually over because the generalization just depends on an induction proof. What we want to prove is that if n is an integer greater than or equal to 2, then we can negate a disjunction as follows. Not P1 and not P2 all the way through not Pn. And the corresponding statement for conjunctions is P2 and all the way through Pn. Now we have not P1 or not P2 all the way through not Pn. You can see how this is a generalization because we proved this just a moment ago for n equals to 2. So n equals to 2, which we proved, is the base case. And I'll show you what the trick behind the inductive step is. We let P2 or P3 all the way through Pn equal to Q. So now we can actually use the base case in the inductive step. This is how we do it. Not P1 or P2 all the way through Pn is logically equivalent to not P1 or Q, and now we can use the base case to get not P1 and not Q, and this is not P1 and not P2 or all the way through Pn. And now we just use the inductive hypothesis. Because there are n-1 statements here. So we can say that this is equivalent to not P1 and not P2 and all the way through to and not Pn. So that proves the generalized De Morgan's law for disjunctions, and the conjunction proof is symmetric to this one. So that proves the generalized De Morgan's laws. And I just want to leave you with one more idea, which is De Morgan's laws for quantifiers. I'm not going to prove these, but it's good to know them. If we have a universal quantifier, then we can negate it as follows. We turn the universal quantifier into an existential quantifier, and we negate the predicate. Similarly, if we have an existential quantifier and we want to negate it, then we flip it into a universal quantifier and we negate the predicate. Okay, just think about the meanings of these and they'll make sense to you, because if you're trying to say the opposite of something is always true, then you're saying that there exists a case where it's not true. And if you're trying to say that the opposite of there is a case where something is true, then what you're saying is that in every case it's not true. Let's do a quick review. We started off with the definition of logical equivalences. Then we stated De Morgan's laws. We proved De Morgan's laws over here using truth tables. We then stated and proved a generalization of De Morgan's laws to n propositions. And finally, I showed you De Morgan's laws for quantifiers. Thanks for watching, and I'll see you next time.